Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Aster Taylor with us today. Hello, Aster.
Hello, Frank. Frank, how's it going?
I am doing awesome on this December 16th of 2024. And I'm in Phoenix, and we are definitely in our winter mode. So we get kind of cool in the morning, in the wee mornings, and then we'll warm up to something very pleasant in the afternoon. So it's just the
Yeah,
brutal, it's just a brutal Phoenix winter, you know.
yeah, the famously brutal Phoenix winter.
That's why we get all these snowbirds coming down.
Yeah, exactly. Yeah,
And Aster, go ahead.
Ann Arbor's pretty nice this time of year as well.
Ann Arbor, I
Um,
was going to ask, but do
yeah.
you have snow on the ground?
We did as of yesterday. We do not anymore. It's 40 degrees down.
Wow. Yeah,
It's been a warm winter, honestly.
no climate change here. Yeah.
No, absolutely not.
Very
But it's
cool.
been nice.
Aster, what's your present position there at Ann Arbor?
I'm a second year graduate student in the Department of Astronomy. Finishing up my second year,
Cool.
and yeah.
Very cool. So you all done with classes? Now you just Arbor
No, it's got one more semester.
one more. Okay, very
One more
good.
semester, and then I'll be
Very
done.
cool.
And then I'll be just doing the work for the rest of
There
the
you
3 years.
go. ABD. All but dissertation. Yeah, yeah.
Exactly.
And Aster, what is it that you like to do for research?
I work on a bunch of different things. A lot of the work that I do is on giant planet formation and stuff like that. But the work that I will talk about today, that is stuff I started in undergrad and still work on, is I work on small body dynamics and
Cool.
the solar system, small objects and how they move and their non-gravitational accelerations in particular.
Very cool. And that
Yeah.
is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Strong non-gravitational accelerations and the potential for misidentification of near-Earth objects. And Aster, take us away.
All right. So as you said, this is an article about strong non-gravitational accelerations and near-Earth objects. Before we begin, I do want to thank my various co-authors, Daryl Seligman and everyone down the list. Daryl Seligman was my advisor in undergrad, and has been a close friend and collaborator since then. And then, of course, Matt Holman and Peter Varish and Davide Farnocchia have been extremely helpful in the development of this article.
Cool.
So this is the basic idea behind this article is that we now have seven, and as seven is the number in the article, it has moved up to 12 as of earlier this week.
Woo.
There was announcement of five more dark comets, which
Cool.
are near-Earth objects that have no detectable coma, but a significant non-gravitational acceleration.
Okay.
And so the implication from that non-gravitational acceleration is that there is an outgassing on these objects.
Yes.
It is sufficiently large in magnitude and in sufficient and out of plane that we don't think it's a radiation effect. We
Okay.
think it's an outgassing effect, but we
Okay.
can't see any coma, and they're in the near Earth environment.
Right.
So
Cool.
and you only detect these after many decades of observation of astrometric observations of these objects because the non-gravitational accelerations are so small, you need to see them over several different apparitions in order to actually detect the motion in the orbit that comes from the non-gravitational acceleration.
I'm with you.
So the idea that we sort of came into with this was, well, one of the important processes in being able to actually do that is knowing that it's the same object,
Ooh.
because you'll
Right.
see an object and then you'll see it again 5 years later. And if you think it's a different object, you're not going to know that it not had non-gravitational acceleration.
Right.
And actually, that was a thing that happened for one of these dark comets. It's still listed in the Minor Planet Center as two objects, but it turned out to have just been one that was misidentified as two separate objects due to
Okay.
this acceleration. And if you've got the acceleration component, then it fit it beautifully. So the idea was, okay, is this something that happens commonly? And what is the and you can imagine that non-gravitational accelerations are going to tend to move these orbits. And how far do you need to move an
Yes.
orbit before the algorithms stop thinking that it's the same object and start
Right.
saying, it's a new object that we've not seen before. Let's keep counting it as a new object and completely missing the fact that there are higher non-gravitational accelerations
Got it.
than you would generally expect.
Okay. Cool.
That's the sort of conceit behind this whole article.
Uh-huh. I'm with
Um,
you. Hmm.
That's the general idea. And so what we did was we took a we looked at a bunch of dark comets, we added non-gravitational accelerations, we made faux observational plans, we made faux astrometric measurements, and we saw essentially how much do you need before you start breaking in these objects.
Okay.
And the answer is more than you would generally expect. I'll give you a quick summary that the answer is more than you expect, and it's
Okay.
not actually that big of a deal. But
Okay.
it's a possibility, and as we get more objects, they become more of a possibility.
Hmm.
So let's start scrolling a little bit.
Sure. Dark comets. There we
Let's go and take a look at figure one, I think.
go. Okay. We'll take
Um,
figure one. Let's
we'll
take a
skip
look
some of these equations because they're very
at
general. We can look at, it doesn't actually matter which of these panels we look at. Let's look at the top one just for, without loss of generality, let's
Okay.
look at the top one.
Okay.
So this is a specific dark comet. And what we did was what we're looking at here is how far on the sky does the object's position change
Yes.
if you had a gravitational acceleration versus a gravitational acceleration plus a non-gravitational acceleration.
Okay.
So essentially, we add non-gravitational accelerations of the magnitude marked there in the direction marked there. So A1 is radial, A2 is transverse along the orbit, and the A3 is out of the plane of the orbit.
I'm with you.
And we run these simulations for 50 years, and we see how far off of their expected positions do they move in that time.
Yeah.
And it depends on the actual acceleration, and it can be as large as 1,000 arc seconds.
Yeah, I was gonna say it's
Uh,
pretty large.
it's
Yeah.
pretty large, and those spikes happen actually during apparitions when you get close,
Yes.
because obviously as the physical distance is roughly continuous, but as you get farther and farther away, as you go out to farther away from the Earth, the distance on the sky gets quite small. As you get close to the Earth, it gets quite large again, and
Right.
so those spikes in the non-gravitational accelerations are when apparitions happen.
Cool.
That's when you can actually observe them. So we'll be seeing it at these spikes.
Got
And
it.
the implication of this is that, you can get quite large motions within a not unreasonable time frame, right? 10 years, you can get over 100 arc seconds of motion.
Mm-hmm.
And depending on the non-gravitational acceleration. And that could be an issue for these algorithms.
Yes.
Let's find out. So
Okay.
we
I'm
then
with
did some similar work. Let's look at figure two now.
you.
The other panel in this figure is exactly the same, just for a different object.
Mm-hmm. 99,
Uh,
86.
and you can see the apparitions are slightly different periods and all this sort of thing. But we can look at this over different time scales.
Sure, and each one will be a little unique there for sure.
Yeah, it depends so heavily on the objects, which is why we did this.
Okay.
For this figure, we generated a synthetic population of near-Earth objects
Okay.
with some sampling from larger scale simulations of near-Earth objects. I believe we used Nesvorny 2017, but I could also have been uniform. I genuinely can't quite recall. But we took a bunch of fake near-Earth objects, ran them on orbits, added non-gravitational accelerations of different magnitudes, and said, after a certain apparition period, how far have they moved?
Right. Okay. Okay.
And this is the plot of this. These are the most significant ones. It doesn't really depend at all on the other orbital parameters.
Yeah.
But it does depend on the semi-major axis and eccentricity, relatively significant. And the color here is how far the object moved on the sky after 10 years of integration.
Okay.
For just all these different objects. And you can see there's some variation, and that's from the fact that apparitions are different. But in general, you can see that for farther out our objects,
yes,
and for larger non-gravitational accelerations, you move farther. And the white contours here show 10 to the 3 arc seconds, which we expect to be. That's sort of chosen arbitrarily as a number that seems sort of big enough to be significant.
Yeah,
it's 10 to the 3 arc seconds is a pretty big distance on the sky. So, we don't actually know. The algorithms depend on which direction those 10 to the 3 arc seconds are, et cetera, et cetera. But this is showing that for certain large non-gravitational accelerations and in certain orbital parameters, you can get quite large on-sky distances. And that's what you expect. The question, though, is if you can actually link them back up. So let's scroll down to figure 3 now. I'm just going to go through all the figures.
Relatively insensitive on the eccentricity. They're fairly flat.
relative isn't sensitive on eccentricity, even
Yeah.
less sensitive on all the other parameters,
Yeah.
which is why
Yeah.
I didn't show them.
All good.
Because they're
All
extremely
good.
sensitive. Oh, and by the way, in the appendix, this is for just transverse non-gravitational accelerations
Ah,
and for integrations of 10 years. In the appendix, we show similar figures for the other two directions
okay.
and for 10 years and for 1 year integrations.
Ooh,
So
okay.
there's 5 figures in the appendix covering out of plane, radial transfers out of plane on 1 year integrations and radial and out of plane on 10 year integrations. This is just the most significant effect you can get.
Okay. Do check those out. Do check those out.
Let's
Okay.
check this out.
So,
So we then look at the minor planet centers linking algorithm.
mhm.
Peter Varish was extremely helpful in this one because he was responsible for doing all the linking algorithms. Different linking algorithms are used by different authors, and there's a lot of variety in making an observation and trying to connect that back up to a previous object. So
Uh-huh.
we didn't know what to do a big survey of all the different possible algorithms. But this is the one that is in use at the MPC. If you just
Yep.
put an observation up on the MPC, they will run this algorithm to see if they can identify it as a previous object.
I'm with you.
So that's what we're doing here. There are two different elements to this whole thing. This is actually, I believe, the first time that the linking algorithm has been described in a paper, just because the MPC doesn't talk about it very much for some reason.
Yeah, yeah.
According
Yeah.
to Peter
Yeah.
Barish, this is the first time it's been written about. But the
Cool.
general idea is that there are two different mechanisms. The first one, it will take all previously known orbits and do a Keplerian integration to the time of observations
Okay.
and see if it's close enough to fit.
Okay.
If the on-sky motion vectors are aligned, and if the previous object's orbit is within 2 degrees of the new observation,
Okay.
that's counted as a link.
Okay. I'm with you. Mm-hmm.
2 degrees is, so not 2 degrees, 2 arc seconds. 2 arc seconds is still pretty big.
Yeah, forever.
But that's the criterion.
Okay.
And then if that works, that's counted. If it doesn't work, then you wait for more observations of an object to appear during a single apparition.
Okay.
And if you see objects appear in that single apparition, if you get enough observations, you can then put an orbit through that
Yes.
and compare that orbits and uncertainties of that orbit to all previously known orbits.
Good. Okay.
So in this one, you're just comparing Keplerian orbital elements.
Uh-huh.
And if they get close enough, then you say this is definitely the right object.
Okay.
And if you get nothing, then you say this is a new object, and we count it as a new object.
Okay.
So we then took 1,000 NEOs that have multiple apparitions separated by less than 15 years, and the 15 years is just put in there for convenience.
Right.
I don't want to run orbital integrations for longer than 15 years for 1,000 objects. It's quite a lot.
Yes.
We then run all these simulations, get fake observations with certain cadences that are chosen just to be sort of generic. It depends very heavily on the cadence, but this is somewhat random. We do a couple every few days, do all these. And then we generate tracklets with both gravity-only orbits, and we generate tracklets with logarithmically spaced non-gravitational accelerations. So
okay.
each object, we say, here's where it should be if it was gravity, and then here's where it should be if a non-gravitational acceleration was operating.
Okay.
And then we feed all of these observations into the NEO linking algorithm and say, what fraction of these can you actually match up?
Right, because you know the answer. Yep.
I know the answer. I know which ones are real. What fraction of these can you actually get right?
Uh-huh.
So if you scroll down to figure 3, the fraction, by the way, is reported in table 1. And then figure 3, and you'll notice, by the way, that some of these numbers are bigger than 1. That is because of statistical randomness in whether or not you can actually make an orbit.
Got it.
So for some of these, they couldn't make it. The algorithm just decided that it couldn't make an orbit for the ones that didn't have gravity, and then it did it for one more that did have a non-gravitational acceleration. Great. And that statistical random chance inherent in the algorithms, we think.
Okay.
But you can also see that by very large non-gravitational accelerations, you start to lose these, right?
Very large ones.
So at this table, by 10 to the negative 7 AU per day, you start to lose but it's about 99%, and then it starts to drop off to 70%. For transfers down to 1%. by 10 to the negative 7 AU per
Right.
day. And that is I'll say that that is a very large non-gravitational acceleration.
Indeed.
10 to the negative 7 AU per day squared is quite big. The first interstellar object, Oumuamua, had a value of about 10 to the negative 6.
Yes.
So it's big, but it's not unreasonably large.
Mm-hmm. Mm-hmm.
Now, 10 to the 6
Actually,
is 10 to the 6 is quite big.
here. Yeah.
Did I
Yeah.
mention?
Yeah.
Yeah,
Yeah.
I did. It must have been somewhere.
There we go.
Yeah, there we go. 10 to the negative 7, sorry, 10 to the negative 7 AU per day.
Good. 2.5.
7 plus or
Okay.
minus a bit.
Uh-huh.
But regardless, so that's, bigger than the value we're looking at here. This object there's a very high probability that it is not linked on successive observations, even if it was not hyperbolic.
Okay. Yes.
It's on a non-hyperbolic trajectory and has a non-gravitational acceleration, you won't see it. Probably.
Yeah.
Figure 3 is showing the fraction of objects that, this is similar to the previous one. This is the fraction of objects that have an on-sky change of at least the magnitude given on the x-axis or bigger.
Okay. Okay.
So
Okay.
it's somewhat of so it's a cumulative distribution
Yes.
where every object has an on-sky change bigger than 10 to the negative 2 arc seconds.
Cool.
Very few of them have on-sky changes bigger than 10 to the 5 arc seconds.
Right.
But we're looking at essentially, for a given magnitude of acceleration, how many objects are actually moving at least this far.
Mm-hmm.
And depending on what your cutoff is and all this, it can be a decent fraction.
Mm-hmm.
The big one is that if you have very large non-gravitational accelerations, you cannot link that object up correctly, we think.
Right.
Well, at least given
the cadence of the observations.
These are just the ones where you say, here's an observation that we've seen, take an orbit, run it through, how close does it get? Is it close enough that we match it up? And the answer is, for most of these, no.
Okay.
For very, very large ones, no.
Does it matter a bit what the cadence of the observations is? Right? Like if you're observing.
It does. Yeah. I mean, so we assume the cadence is approximately, well, for these, we actually knew what the cadence was.
Yeah.
Well, we knew it depends very heavily on the apparition time. The cadence also matters, but it matters a little bit less.
Yes.
Because it just gives you uncertainties on the velocity distribution for this one.
Okay.
The apparition time is very important. It's how far between observations you actually get.
Yes.
So cadence is in an apparition you can observe, every day. Apparition time is you observe it now when it's close to the Earth and bright, and then you'll be close to the Earth and bright again in 5 years.
Okay.
And that's when you can see it again.
Okay.
So the apparition time matters, and we accounted for that. But even if the dark comets are at 10 to the negative 11, 10 to the negative 12, by even an order of magnitude larger than that, you're still getting pretty good accuracy in being able to match up these observations. Cool. So we're not expecting to lose a lot of these.
Okay. The
one that is more important, and this is the first, actually, let's just say it like this. This is the first filter. This is the first filter of matching up objects. Mm-hmm. This is to do a Keplerian advance of the orbit. Does it match anything?
Yes.
The second way to do it is then to fit an orbit through those observations and match it up to previous orbits and see if those work. We also tried that for all these objects.
Okay.
If you scroll down, we also tried that for all these objects. And for that one, the vast majority of the objects work out just fine. This is talked about a little bit above. But the vast majority of these objects are linked to previous objects, are linked to the original orbit. So they're all connected up correctly. However, the uncertainties for the observations that are made are very, very small. Sorry, very, very large. So we have very few observations in a new apparition. We have very large uncertainties in the orbital parameters.
Okay.
And while we checked, do they match the actual orbit that we know to the uncertainty? The answer is yes. But they also match a lot of other objects to the uncertainty.
Okay.
And as you get more and more precision, and as you get more and more objects, it's going to be harder. And as you narrow that down, the orbit parameters will have changed. And so there's going to be a question of, do they change enough that they start falling closer to another object or start falling on their own? And the answer is we don't know that because it depends. We haven't run the simulations.
Get crowded. Okay.
It can match up. It can match them up too well because we think it can match them up to more than one object pretty easily.
Ooh, yes. False positive.
And then you just get more observations and hopefully narrow it down. And then you get to one object, and that's the one you take. Or you narrow it down so much you get to 0 objects, and then you just say it's a new object.
Okay. Okay, I'm with you.
So we think that's what happened for this one object that we observed that we did link up correctly.
Okay.
But then there's an important question of, can we do that again? We did that once for BL65. I don't remember the number.
2010.
It's written, whenever it's mentioned BL65, you scroll down a little bit, that should be up a little bit.
2010, two.
2010, there we go, 2010 BL65. We did it for that. Can we do it for other objects?
Okay.
So we searched the entire set of NEO objects and tried to find unlinked pairs again. We used a variety of different algorithms. We checked to see if they were close in orbital parameter space, if their Keplerian elements were the same. We checked to see if they were close in angular momentum space, so that their angular momentum vectors didn't change.
Okay.
And then we developed these constants of motion that depend on the same major axis and eccentricity, and that depend on the other Keplerian orbital parameters. And if you take the most simple form of non-gravitational acceleration, where it is a constant number times a 1/r² dependence on the radius, and that on the heliocentric distance, and then that goes in a single direction based on the orbit. If you do that, these constants are unchanged over those orbits. If it moves under that motion, you can calculate, natural log of eta minus 1 squared over a eta squared. Eta is the square root of 1 minus e squared, and that will not change for anything undergoing that sort of acceleration.
Cool. Constants of motion are always a good thing. Okay.
There's a lot of assumptions inherent here. You're assuming it's not too big, because if it is too big, then it moves over the course of the orbit, which is very annoying. So these are orbit averaged. It has to be small enough that on a single orbit, you can say that it's the same orbit on one orbit, but over several, it will actually move.
Okay.
Otherwise, this doesn't work at all, and that's just an unfortunate fact. It's significantly harder to derive one that does work in that circumstance. But we also check these constants of motion.
Good.
And so we looked at all the near Earth objects, made a tree of all their different, of all the closest tree for every single object in these 3 different parameter spaces, and checked the closest few hundred, ran these through fitting algorithms with Davide-Farinaci's fitting algorithms to see if we could actually match up these objects to some statistical significance. All of these mechanisms found the previously known case. They all found 2010 BL65 and 2021 UA12.
Good.
They all said that was one of the closer pairs, and if you ran it through the fitting, it said this is the same object.
Cool. Okay.
It's good. That works. It found no other objects though.
Okay, so no false positives.
So no false positives, and no true positives. Well, one true positive, no
one
false
true.
positives.
You got one, yeah.
We got one. We got the one. We won the one. No false negatives. We think.
False negatives. Okay.
Kind of hard to know, right? There's one object that we know this works for, and all these algorithms found that one, and they said here's some other ones that it could be, but none of them were real. Okay, and that makes sense. But that implies that there aren't all these pairs sitting out in near Earth object space. So the whole thing is, is it possible that there are pairs of objects that are unlinked because of non-gravitational accelerations? And if you add non-gravitational accelerations, they'll get linked back up together. And the answer is that happened for one pair of objects, and we haven't found another one. Okay.
Starting.
So implicitly, the linking algorithms are then pretty good since they're not finding any other ones. Okay. But it's really hard to know. We've made a lot of assumptions that these are small non-gravitational accelerations, and that they are, and that we've made assumptions based on that. And we are assuming that if there are pairs, they're pretty close together, and that may not be the case. But either way, we think that the algorithms appear to be doing pretty well at finding these objects and at linking them up, even if there are non-gravitational accelerations. Okay.
Go ahead.
In the future, as we get, LSST and Rubin comes online, and we get a greatly increased census of small bodies, we are expecting that the number of objects goes way up, and this may become an issue.
Yes.
As we
Yes.
get more objects, the likelihood of linking up two objects incorrectly and then
It's going to
accidentally
increase.
narrowing it down too far becomes more common,
Yes.
but we're not quite sure.
Okay. We
We
shall
haven't
find.
been able to check that, but we expect that this is not an issue right now. It may become an issue in the future, and it's certainly happened at least once in the current solar system. So that's what we're working with.
Okay.
We would love if we could find more objects that were not linked successfully in the first algorithm, but these
Okay.
algorithms seem to be working pretty well. There are other algorithms that also work very well that we suggest people use. HelioLink, we think, works very
Okay.
well on this problem. And also, if you just incorporate non-gravitational accelerations, this stops being an issue.
Okay.
If you run your models with non-gravs, you'll always be fine. You might not always
Sure.
be accurate. It's a lot more computational time, and it can be annoying. But if you run them with non-gravs, you'll always be right.
Okay.
At least for this.
How about for large gravitational? Do the current algorithms work well with large?
For very large ones, we don't think they do.
Okay.
For very large ones on near-Earth objects, we don't expect to see very large ones on near-Earth objects
Yeah.
because there's not that many very near-Earth comets. I mean, Oumuamua is a bit of an outlier because it comes from very far out of the solar system, just comes blasting by.
Yeah.
So it's like if you had something of similar magnitude, you would have trouble finding it.
Okay.
If there was something orbiting around the sun at, let's say, an AU and a half, and it had a 10 to the negative 7 transverse non-gravitational acceleration, you would have a lot of trouble finding that object.
Okay.
We don't believe that such an object exists, but we wouldn't exactly know if there was one,
Right.
because we wouldn't. So
That's great.
it's sort of like we don't know about anything like that. We wouldn't,
Right.
because we wouldn't find it. But also we would know if it was much farther out. An object at
Yeah, true.
like 5 AU is much slower, and it's far enough away that the change in on-site position is smaller, so you can you're more confident that you can link those up correctly. And so you'll probably find that one, and we don't know of anything out there with such a large A2. And we don't expect there to be more non-gravitational accelerations in the near Earth environment.
Okay.
So physics and experience tells us that such an object probably isn't there.
Okay.
If there was one, we couldn't find it. But
helpful.
if it was one, we couldn't find it with current algorithms.
Okay.
If you use but admittedly, like we also checked and we couldn't find any. Because if there was one with non-gravs, we would have found, and it wasn't ridiculously gigantic, we probably would have found it in our parameter search.
Right.
And our parameter search didn't find anything.
Okay. Okay.
So there probably is we ran fits for all the best fitting, the closest pairs. We didn't find any non-gravitational accelerations on those objects. So we're presumably fine. And then we discuss the various possible implications of this and what it could mean if this is a problem, etc. If it is a problem and there's a lot more non-gravitational accelerations in the near-Earth environment, then that has implications for volatile delivery and Earth defense and all these sorts of fun things that happens whenever you have a lot of hydrated small bodies in the near-Earth environment. Yeah. But that occurs if this is a bigger problem than we think. A lot of this could have been a problem, and we showed that it wasn't really that big of a deal. We are not missing a lot of these objects
now,
which is great. It's a little bit boring, but it's scientifically useful, and it's good to know that we're not messing everything up.
Right. I sometimes quote null results unquote are actually pretty darn valuable.
Absolutely.
And it's probably, well, we'll cover it here in a sec, but I bet it's probably maybe a time dependent answer too, right? Might be in null now, but it may not be.
It may not be after LSST.
When Rubin turns on.
Yeah. When Rubin turns on, we'll get a lot more, and it's going to make it worse.
Yes.
We don't know how much worse. It depends on the algorithm, but
no. Okay.
Cool. Yeah. I think that's everything that I have to say.
Very cool. Very cool. Aster, I want to thank you so much for walking us through your very awesome APJ article. Very nice. Thank you.
Thank you very much.
Yeah, and you kind of touched on it a little bit there. We hinted on,
Cool.
the tsunami coming with Ruben. And I'm
Mhm.
just kind of curious about maybe, what the next steps might be once Ruben turns on, or what and where we go from here. Are there, so you mentioned different algorithms that one could try.
Mhm.
Are there other ones that one may want to try in a couple of years? Um,
Yeah, for
are
sure.
there other theoretical models one might want to go after? Are there additional observations to help pick up even more dark comments beyond Rubin, and so on? So just sort of next steps. Where do you think we go from
Absolutely.
here, given the
Absolutely.
published article?
So I think number one, we definitely want to check the heliolink algorithm, which is the one that is planned to be used on Rubin to find small bodies.
Oh,
Um,
okay.
Currently, we checked in here the MPC algorithm, which works pretty well.
Hmm.
Heliolink is a different algorithm that I suspect is going to work a bit better, but I haven't checked it. And so we would like to be able to check Heliolink and make sure that that one's running well. And
Right.
if it's not, then we would want to add non-gravitational accelerations to the algorithm to be able to fix these issues
A
before
priori.
Rubin turns online.
Yeah.
Rubin's going to give us a lot more observations. It won't give us a ton more objects across apparitions in the beginning
Okay.
because it takes several years to
Years.
find
Right.
apparitions. So
Right.
you
On a
turn
run.
on Rubin, you find a ton more objects. 5 years later, you find the same objects again, and you can make linkage issues. But we'll find uh, new apparitions of old objects in Rubin that, and we'll get a lot more of them. That may
Cool.
become an issue.
Cool.
We also would like to find more dark comets. A lot of that requires more astrometric observations. Rubin will be very, very helpful for that, just giving us, as I said, more apparitions, a larger survey, getting
Right.
us all these outputs.
Right. You can do follow
And
up.
then a lot of it is just running the truly gigantic database of small bodies that currently exists through fitting algorithms to try to find them. And that is what my Davide Farnocchia and Daryl Seligman did for the PNAS paper that came out, PNAS paper that came out earlier this week, was finding 5 more of these
5 more.
objects through running them all through algorithms, through
Wow.
fitting algorithms and doing this.
That takes a
And
little.
then, getting more observations of near Earth objects to try to constrain volatile presence on the dark comets and all this would also be useful. It's not particularly related to this paper, but if we knew that non-gravitational accelerations were more common in the near Earth environment, that would give us a lot more information on uh, how likely we think this is to occur. What
Yeah.
fraction of objects could have this error on it, and how common is it, and what's
Yes.
the probability that we link them incorrectly.
Cool. Very cool. Well, I'm predicting a very awesome PhD thesis. How about that?
We'll see how it goes. Thank you
Very.
very much.
Aster, I want to thank you so much for walking us through your very awesome article. Nice.
Thank you. Very happy to.
And that will do, everybody. That will do, everyone. And I hope this made your astronomy day, particularly your non-gravitational astronomy day, just a little bit better. And we will see you on the next one. Bye-bye.